are going to start the lecture Advanced Reaction Engineering. So, today we will discuss about the differential reactors and rate of reactions, catalyst deactivations. Okay. So, already we have discussed about the packed bed reactors. So, packed bed reactor, that is the large scales or bulk scale catalyst we can put inside of the reactors, we can conduct any reactions. So, now we discuss about the differential reactor. So, what is differential reactors and why it is important, and so how means experimentally, means if we want to find out the rate of a particular reactions in gas and solid phase reactions. So, in that case how we can find out the rate of the reactions experimentally. So, that we will discuss. So, here you can see in the right hand side, this is a packed bed reactor that already we have discussed. So, here this is the reactors. So, here we have charged a bulk amount of the catalyst 10 kg, 20 kg, 60 kg of catalyst we can charge inside of the reactor, and then so this is the feed we are charging feeding here at a particular concentration of the reactant, that is charging Ca0, Fa0 molar flow rate, one volumetric flow rate, that is charging, and it is entering inside of the reactors, and we have taken W amount of the catalyst, and then from the bottoms we are getting the products. Okay. So, this is the concept of the packed bed reactor. So, now here this is the differential reactor. So, in this reactors here you can see this is called differential reactor. So, why you can say here W amount of the catalyst was taken and length was from here to here, that length was also Z you can say, okay, or Z or L also you can say. So, now in this reactor what is the basic difference? Here small amount of the catalyst you have taken. So, delta W amount or delta X or delta the length of that particular thickness, it is very small, close to 0. You can say here 10 kg of the catalyst was taken, it has a significant length or height or amount of that weight of the catalyst bed, but here if you take very small amount catalyst, the same catalyst we are taking, but very small amount, it is close to 0 or maybe 10 milligram catalyst you have taken, here 10 kg of the catalyst, here 10 milligram of the catalyst, very small amount of the catalyst you have taken, and we are making it into a wafer, okay, wafer or thin film we are making, okay, the catalyst wafer or disc type of circular disc that is placed inside of the reactor, and then the same reactions we are conducting here, reactant is charging, we are maintaining desired temperatures and pressures. So, what would happens when reactants A will these reactions if we conduct, so then reactants A and B will be passed through this bed, and product corresponding C and D, it means reactions will take place and C and D product will form, okay, if we maintain the same temperature. But here the amount since the catalyst amount was very small amount, then conversions would be also very low, conversions will get. Here 0 to initially it was conversion was 0, and when we are charging 10 kg of the catalyst, let us say 60% conversions we are getting. So, here we are putting let us say 10 milligram of catalyst, very small amount of the catalyst as compared to the 10 kg. So, here very small amount of the catalyst. So, then reactants Ca0 to Ca, that is the changes of the concentration of the component A, that also would be very significant, signal is very small changes of the concentration. So, we can say this almost these two Ca0 and Ca would be the almost same value. So, but there is some changes since catalyst was there, the conversions would be there, product formations also would be there. So, this type of the arrangement is called differential reactors. Okay. So, this type of reactors are used to determine the rate of the reactions as a function of concentration of the reactants or concentration of partial pressure of the reactants, that in terms of concentration or partial pressure we can express. So, that way means to determination the rate of a reactions, means for a differential reactors, whenever we are going to design pressure drops or other things we are going to measure, then rate equation is required. So, how to find out the rate constant rate equation? So, for that experimentally this type of reactor is required, and same reactions we can conduct, and based on that experimentally rate we can find out. Okay. So, here few assumptions and criteria for this particular reactors, where we can say the reactor is a differential reactor. Here the conversion of the reactant is very small. I said the conversion is negligibly or very small, but it is not 0, but some conversion is there 0.001 conversion is there, some conversion is there. So, this is the criteria of this type of reactor, differential reactor, conversion should be very low and reactant concentration throughout the reactors is constant. We are assuming that throughout the reactors there is no changes of concentration, means anywhere. In case of the packed bed reactor, the concentration individual points would be different, conversions is different, concentration is different, rate would be different, but in case of the differential reactor, throughout the reactor the concentration is constant, therefore the reactant concentration throughout the reactor should be the constant. So, here I said here is some differences is there. So, initial concentration and final concentration of the reactant A, some changes are there. So, that would be the difference, and based on that we can set how much reactant that is converted. So, that is means primary criteria for a reactor should be differential, and the reactor is gradientless, reactions rate is uniform within the bed, and reactors will operate isothermally, means in any point of the reactors would be the same temperature, no reactants will bypass or channeling. So, here in this reactors, when the reactant will come and that will pass through this bed. So, there is no pores here inside of the beds, channeling possibility is there, but this experimentally when you are going to do any or conduct any reaction, in case of the differential reactors we are assuming that no reactants bypassing or channeling is there. So, all reactant is passing through this wafer and catalyst should not decays rapidly, means when a reactor means the reactions you have to choose such a way, but within that stipulated times you have to conduct the reactions as if there is no catalyst decay. If catalyst decay is there or catalyst deactivity is there with the means proceed of the reactions, then we cannot find the actual rate of that particular reactions. Okay. So, sometimes in this type of analysis product streams is difficult to analyze due to the less amount of product forms, means here we said conversion is very low. So, sometimes this type of reactor what are the problems are there, means in concentrations of the product is very small amount it is forms, means negligibly small, means conversion is low. So, therefore, sometimes it is very difficult to detect that product, that is if there is suppose we have a GC gas chromatography analysis. So, there if you want to analyze that product whether it is form or not, so then it would be very low concentration, therefore, it would be sometimes we cannot measure that quantity. Okay. Quantification is very difficult sometimes. So, let W weight amount of the catalyst that was taken, so this is the minus R prime, this is the rate of that particular reactions per unit mass of the catalyst. So, assume the differential reactor is the gradientless and the design equations that you have to use, that is similar to that of a CST reactor design equation. So, here the material balance we are doing. So, at steady state flow in, flow out, rate of generation, that is accumulations, that is the general material balance. So, here Fa naught, that is the inlet molar feed rate of component A, that is the exit part component molar flow rates of A, and that is the rate of generations, means R A prime into delta W amount of the catalyst. Here W is the catalyst. So, here you can for differential reactor delta W amount of the catalyst that we have to take. So, then this is the design equation for differential reactor minus R A prime equals to F n naught minus F A E by delta W. This is the design equations. So, now V equals to V naught, if we consider that reactions is operating isothermal conditions, there is no volumetric changes, flow rate changes during reactions, then V equals to V naught we can put, and we can write these equations into this way, volumetric flow rate, molar flow rate in terms of volumetric flow rate and concentration we can express. So, then we can take out V naught, V equals to V naught we said here, so here we can substitute and then we can take out from the first bracket. So, V naught into C A naught minus C A E. C A is the, that is the outlet or exit concentrations of component A, or we can say V naught into C P by delta W. C P, what is the C P? C P is the concentration of the product. Okay. So, or that reactions we can write this way also, this rate equation similarly we can write. Okay. So, here let us say this is the reactant and this is the reactions, A is converted into product, stoichiometric coefficient is A and P. If we assume that component A and P both are same, means 1 1. So, then these equations we can write this way. Okay. So, now this is the rate equations for the differential reactor. So, here's right hand side, these are the components. If you are able to know, then rate for individual reactions using these reactors, we can find out at different reaction, different temperatures, at different amount of the catalyst. That way we can use this differential reactor for that particular reactions, we can find out the experimental rate. Here's one examples I will give. So, how to really or experimentally or laboratory scale how we can find out the rate of formations or rate of disappearance of the reactants that we can find out. So, here's one example we have taken. So, here hydrogen plus CO that is giving methane plus water. So, hydrogen plus CO. So, hydrogenation reactions of CO carbon monoxide, that reaction, this is the reaction. So, here if we conduct the experiment using a differential reactors, these reactions we are conducting. Okay. So, let us say for this particular reaction. So, here we are taking 10 gram of catalyst, and so here we are charging CO plus hydrogen here, and bottoms we are getting CH4 plus waters we are getting. So, okay. So, here 10 grams of catalyst was taken, and here volumetric flow rate of total volumetric flow rate, that is equals to given here 300 dmq dmq per minutes. Okay, dmq per minutes, and weight of the catalyst was 10 gram. Okay. So, now catalyst weight we know that we can put it here, and this is the design equations. Here V naught also we can put it here. Here the concentration of the methane, that is the product. Okay. So, once we run that system for this particular reactions, these are catalyst weight is the fixed, volumetric flow rate is the fixed. Okay. So, here we are just varying concentration of partial pressure of CO and partial pressure of hydrogen, both are the reactants. Okay. Partial pressure for let us say run 1, first times if you conducting a run by maintaining 1:1 pressures of reactants, and total volumetric flow rate is this, then the concentration of the methane, that is the product that we are getting from let us say chromatography is there GC. So, we are measuring this concentration of product that we are getting from the end of the reactor is this. Okay, concentration we can measure. Similarly, for run 2 also under the same conditions. So, here concentration or partial pressure of CO and hydrogen partial pressure remains same, only partial pressure of CO is different, we are changing. So, then rate would concentration of here would be different of methane, since the run is different, CO concentration or partial pressure is different. Similarly, for run 3 also we means maintain the partial pressure of CO is this and partial pressure of hydrogen is this, then concentration reactions would be, conversions would be different, as a result concentration of the products also would be different. So, this is the experimental observation or experimental data for this particular reactions considering a differential reactors. Okay. So, this is the conditions, this is the differential reactors we have used, and this is the experimental observation. So, from this how we can calculate the rate of this particular reactions. Okay. So, experimental rate equation is there for that. So, here V naught delta W, this part is known, concentrations of methane for run 1 we know. So, that we can substitute here. So, then V naught is this concentration of the methanes, that is the product we are getting, that we know, amount of the catalyst we are placing inside of the reactor, that is known. So, then rate of the reactions this particular experimental rate for this particular reactions under these conditions we can find out. Similarly, this is for run 1 we have mentioned, okay, minus R CO at this particular point is 5.2 into 10 to the minus 3 mole methane per gram catalyst per minutes. Okay, this is the rate. Okay. So, similarly, this rate also we can find out, this rate also find out. So, here also 4.4 this part will be different, this concentration part of methanes. So, if we put it this, then rate would be different at this particular run 3 also. Similarly, concentration of the methanes that we are getting for this particular set of run. So, then we can measure the rate of disappearance of CO, rate of that particular reactions is this. So, by that way individual rate or individual runs for the same reactions, the rate would be different, since we are changing some parameters for this particular reaction. So, therefore, the rate also would be different. So, experimentally using these differential reactors for this particular reactions, so rate we can find out experimentally. Okay. So, that is the use of the differential reactor. So, later this equation should be very useful, so that will or this reactor also is very useful. So, that we will discuss more details if it is required. So, okay, next we are going to discuss about catalyst deactivations. Okay. So, whenever we are talking about catalyst, solid catalyst, and we are conducting any reactions, so then it is observed that catalyst deactivates, means deactivate means at the beginning. So, when we have taken the catalyst, we have charged fresh catalyst, reactions at the beginnings would give very good and will get very good conversions. Okay. So, but at the sometimes means when time is proceeding, so it is observed that the rate of the reactions is gradually conversions of that particular reactions is downing, means decreasing. So, under same conditions, means same temperature, same pressures, everything we are maintaining the same under the same conditions at the beginning or after 30 minutes or after 1 hours. If you look or analyze that catalyst, it is observed that the catalyst going to deactivate. Deactivate means the catalyst performance is not good at all. So, then why it is happening? So, that is there are so many reasons. So, maybe whenever we are going to conduct any reactions, let us say cracking, there is gas wells or lube wells cracking, means gas well cracking, cracking reaction is there. So, when high molecular weight hydrocarbons is there, so that is the long chain hydrocarbons. So, if we want to crack, that may be catalytic cracking or thermal cracking if we conduct. So, then what is happens? So, during crackings means large or long chain molecules that is cracked into smaller components, smaller fragments or formations is there, smaller component. So, then some carbon formation, elemental carbons or carbon particles formation is there, that is called coke. Okay. So, that would be deposited over the surface or the active sites are there. So, that is deposited or covered over the active sites. So, once the catalyst is covered with the active sites by the coke that is generated or forms during the reactions, then the active sites is not available to take part in the reactions. So, then therefore, the conversions will be drops, that is the one of the reason. So, others reasons are there, so that we will discuss. So, means that is due to the poisons or maybe sometimes the catalyst we are taken, so that we are conducting or preparing that catalyst that is good for let us say 600 degree centigrade for a particular reactions. If we conduct the reactions above the temperature, let us say 600, we are maintaining 700 degree centigrade, 800 degree centigrade to get higher conversions. So, on that time also catalyst agglomerations is there, means active sites agglomerates, larger particle formation is there, and as a result what would happen in the side of the catalyst, so many mesopore micropores are there. So, that would be blocked. Okay. Once that would be blocked, so what would happen? So, then reactant will not come in contact with the active sites. Okay, that would not reach, that would not diffuse inside of that catalyst. So, therefore, the overall conversions rate everything will drop. So, catalyst deactivate. Okay. So, there are many reasons. So, here you can see that let us say this is the reactions, here catalyst we are placing and we are maintaining temperature and pressure. So, activity here I said that conversions that which drops with the time, y axis conversion and x axis times we are placing. So, at the beginning let us say 0 times and t times, that is let us say 100 minutes. So, here initially activity was very good. So, when conversions also very good. So, fresh catalyst you have taken conversion. So, after 4 hours you can see the conversion is gradually dropping with increasing times. In the x axis time is increasing, means at the beginning conversion was very good, that is expected for any catalyst whenever we are choosing or charging inside of the bed of the inside of the reactor for to conduct any reactions. Then throughout the operations we are expecting that conversions would be linear. Linear means it would follow this, means whenever the time gradually increase conversions lines would be like this, means let us say it is 100% conversion, 80% conversions for a particular reaction, that should be remain the same or constant throughout. But in real case what is happen? In real case let us say this is 60% conversion. So, means after let us say 30 minutes we can say that conversion is same, say 60% conversion is maintained, but in real case what is happen? This is drop. okay, these conversions will drop. So, that is due to the catalyst deactivation. So, catalyst deactivations that is expressed in terms of activity. Activity means let us say this is the activity AT, that is we are expressing catalyst activity. This is the rate at any time and this is the rate at t equal to 0 at the beginning. So, at the beginning the rate would be very high and so once reactions will proceed the rate would be down. Okay. So, activity, that is the ratio of two rates. So, at any time rate at the beginning rate. So, that is the ratio or dimensionless parameter, you can say that maximums it would be 1. So, if a catalyst throughout maintaining the conversion same, then activity equals to 1. So, if it is not, then with along the time the activity also with conversion, that is also downs, means this rate would be decrease, since conversion is decreasing, rate also will be decreased. So, therefore, the activity of that particular catalyst would be decrease. Okay. So, this way activity with along the time. So, it would be natures of this. So, activity we can express the ratio of rates. Okay. So, now this would be useful, this means once we conduct any reactions, for these reactions we have a rate, concentrations, volumetric flow rate, molar flow rate for individual component. So, rate equations we can derive or based on concentration, partial pressure or experimentally rate we can find out. We have discussed about the differential reactor. So, the rate we can find out using that rate equations, experimental rate, and based on similarly when catalyst is going to deactivate. So, that deactivation rate also we can find out. Okay. So, that we will discuss more details. So, here's the rate law for catalyst activity, we can same equations or rate equations whatever this activity and rate. So, we are expressing in this way. So, here this is the activity term and this is the reaction rate constant and concentration terms. Okay. So, this is the usually the rate we can express in terms of rate constant and concentration if there are reactant A and B participate in the reactions. So, then individual reactant concentrations we should put in that equation. So, then minus RAT means that is the rate at any times when the catalyst is going to deactivate or the catalyst system is deactivation system. So, in that case if we want to find out the rate on that particular times, let us say a reactors is there, catalyst will work for let us say 60 minutes. So, 60 minutes after that we have to take out all catalyst from the reactors and again fresh catalyst we have to charge over there for the reactions. So, if we want to that 60 minutes means how long we can use that catalyst for that particular reaction. So, when we have to change the catalyst, so how we will decide. So, that actually this rate will decide. Okay. So, at a particular times means let us say 60 t equals to 60 minutes. So, then the rate would be drop. Okay. So, this is the initial rate and this is the activity, this AT value will change from 1 to 0, let us say. So, here 1 is the activity, very good catalyst, and activity when 0.5, 0.4, 0.3 like that 0 close to 0, then this is completely deactivated catalyst, rate is close to activity is 0, initially 1 and then 0. So, then this part we can put it here and this is the rate part. So, now the catalyst deactivation or catalyst decay rate. So, how can we express R d equals to minus this rate we are writing R d equals to minus dA by dt equals to some functions of AT into K d, that is the deactivation rate constant and some concentration terms. Okay. So, here R d is the rate of catalyst decay. Okay. P a is the some function of activity, it is the function some function and K d is the specific decay constant. Okay. So, catalyst is usually minus R a equals to K into C a C b, we usually write. What is K? This is the reactions rate constant or specific reaction rate or reaction rate constant we can say. Similarly, when catalyst is going to deactivate, when reactions is there. So, similarly specific decay constant, specific reaction decay constant K d T. Okay. So, and HCI, that is the functions of functionality of rate on the reaction species, some concentrations means concentration, that is here concentration or component A and B is there this is in terms of concentration actually. Okay. So, let us say here P is the activity for A1 or A2, so that is the power. So, that is first order reaction, this is for second order reaction. So, the activity this AT we can express similarly the concentrations here we are expressing for A reactions A or B. Similarly, if it is A equals to let us say 1, so then we can say first order reactions like N equals to 1, N equals to 2 equals to second order reactions. Similarly, when catalyst is going to deactivate, the order that also we can say it is a first order deactivation, second order deactivation. So, that way also we can express. Okay. That means this is the in generals means rate catalyst decay rate and activity and then rate catalyst decay rate constant and concentration individuals components. So, how we can write that we have discussed. So, now I said the catalyst when that is going to deactivate. So, there are many reasons I said. So, at the beginning I said that is aging, fouling or coking or poisoning. So, okay, these are the various type of catalyst deactivation process are there. So, means catalyst when we are charging inside of the reactors, catalyst go deactivate. So, here deactivation I said here due to aging or sintering. So, this is our fresh catalyst you can see. So, fresh catalyst is there, this is the pores. Okay. So, whenever we take a catalyst, so there micro pores are there. Okay. So, this is catalyst, consider this is catalyst. So, here this is the pores. So, reactant A or B that will diffuse through these pores and this is the active sites. Okay. So, here is the active sites, here catalyst or reactant molecules will come in contact and then reactions will form, reactions will proceed and then corresponding product will forms that will come out. Okay. So, this is the means the simple diagram. So, how we can express the active sites pores of the catalysts. Okay. So, let us say this is the pores, here reactant molecules will enters and these are the rates, these are the active sites. So, here come in contacts, the reactions will proceed and corresponding product formations is there and then the product will diffuse from the inside of the catalyst pores to outsides. Okay. So, here see here aging or sintering is one of the reasons to deactivate of the catalyst. So, here means this here initially pore diameter was this, but here you can see due to the aging or sintering. So, if we conduct the reactions at very high temperature, so then I said that that pores may be blocks. Okay. So, once pores or channels is blocked, so then due to some agglomerations or these sinterings or aging. So, then if this pore is blocked, so then reactants will not enter inside of this pathway. So, then there will not be proceed of the reaction. So, that is one of the reasons. So, initially smaller particles there, after T times due to the agglomerations small active sites will be agglomerates and forms a larger diameters particles. So, therefore, due to this or blockage of pores, so then catalyst will be deactivate and conversions or rate will be changes. Okay. So, here the second order decay rate law is derived. So, by considering R d equals to K d into A square, that is the decay rate law, R d equals to K d A square. Okay, that is the decay rate law or for the second order means here we are assuming it, you can consider also first order also. So, here we are considering second order decay rate. Okay. So, R d equals to K d into A square and R d equals to we can write minus d A by d t. A is the activity I said, K d is the reaction decay rate constants and here if we rearrange this equation and integrate activity A was 1 when t equals to 0 and activity was A that is at when time equals to t at any time. So, the activity E was A. Okay. So, now if we rearrange these equations and integrate this, in the left hand side the time scale is theirs and right hand side that is the activity is theirs. So, if we integrate and then rearrange we will get this 1 by A minus 1 equals to K d into T or again you rearrange this. So, after rearranging, so you will get A T equals to 1 by 1 plus K D into T. So, activity means for a particular catalyst, if that is the second order decay rate law, that catalyst activity follow. So, then at any time, so these equations is useful, means whenever we are going to find out a catalyst, we have charged a phase catalyst inside of the reactor, and after that I said after 60 minutes we have to again take out all catalyst, that is the spent catalyst or deactivated catalyst, and new or fresh catalyst you have to charge inside of the reactor. So, the time means how long we can place that catalyst inside of the reactor, how will decide. So, using these equations easily we can find out. So, activity of the catalyst. So, K D deactivation rate constant for that particular systems if it is known. So, then with times activity how that would change if K D value or small K D value is known for a this type of deactivations, let us say for a second order deactivations rate it is following. So, K D value is known value, that let us say this is value 10 something, some units are there. So, if we put it, so with times A T we can find out. Okay. So, A T and see here's time. So, if we increase times activity, how that is dropping of that particular system, that easily we can find out or easily measures, means these equations would be useful. So, okay. So, that is systems for deactivations due to the sintering or aging, that is very useful. Okay. So, with the reactions rate or reactions rate constant, concentrations, rate equations, with that deactivations and catalyst deactivation is there. So, that part is also is very important. So, okay. So, that will already know, means how this equation have been generated for the second order reactions, second order decay rate law. So, similarly for first order also we can find out, or fractions order also decay rate law if following second order. Actually means first you have to conduct the reactions for a particular reactor using a reactor, and once we means the thorough study you have to do by we maintain that particular temperature with conducting the reactions, and once we know that catalyst is going to sinter. So, then that study experimentally you have to do in the lab scales considering the same reactions, putting the very small amount of the catalyst, that is the known quantity, and catalyst gradually going to deactivate. So, deactivation part also similarly we have to find out if it is going to by sintering. So, okay. So, that study you have to do, and we have to measure, means the conversions yield how that is coming, means with the changes of the temperature. So, that we can plots, and we can say that the catalyst is not good for long period of times, or maybe after more times it is going to deactivate. Okay. So, today this part we are discussing, or we have discussed. Rest of the part means fouling or coking and poisoning, that part we will discuss in our next class. Okay. So, today just up to this. So, due to the aging or sinterings, how catalyst going to deactivate, and if it is second order reactions it is following. So, then activity and K D and T how they are related, that we have just discussed. Okay. So, thank you. So, today is up to this. Okay. Thank you.